the Technical University of Munich, and today I want to present monitoring concrete pouring with knowledge graph enhanced computer vision. So I want to start my presentation with this beautiful building. Does anyone know which kind of building this is? Quite famous German building. Hamburg, I heard it already. It's the Elbphilharmonie Hamburg. And they planned this nice building with an initial cost of 77 million. However, after 10 years, they finished with a final cost of 800 million euros. And of course, we ask, what happened, right? And as it is always the case with large construction sites, there are like many reasons for it. Like we have many contractors, legal disputes, in this case, very high complexity due to the acoustic requirements. Today I want to focus on one specific reason out of all of them, like uncoordinated concrete pouring. So why concrete pouring? Well, they used a lot of concrete building this building. In total, they used like 63,000 cubic meters of concrete. And the method they were using is crane and skip concrete pouring. And with this method, a lot of things went wrong. Like, for example, timing misalignment, incorrect sequencing, and so on. So we can see there's like a lot of problems involved in concreting. So what is crane and skip concrete pouring? So it basically is very straightforward, a three-step process. So it starts by concrete mixers arriving on the construction site, filling up a concrete bucket. Then this concrete bucket travels, gets lifted up by a crane and a crane hook, and it goes to a certain location where the concrete gets released and formwork gets filled, and we build some building components. And the concrete gets released through a hose, like a pipe, which is controlled by workers usually. So they have a nozzle and fill the formwork. So for this process, as we can see, there are like many resources involved, like for example, the concrete mixers, the crane, then we have the concrete bucket and the workers. You can also have a look at a video of this process, right? Concrete mixer arrives on the construction site, then the concrete bucket gets filled up, it travels to the specific location, goes back and forth. So now that we know about this process, the question is, of course, why can it cause delays and cost overruns, and why is it so significant for our construction projects? So first of all, as you can see on the bottom left image, there are like concrete mixers queuing up, and this happens quite often on construction site that due to some delays, we get further delays. And the first reason this happens is that like basically all of these resources are occupied during the concrete pouring process. So concrete mixers may block the entrance road of our construction site, hindering other resources getting on the construction site. Then the crane is occupied during this process, right? On many construction sites, we only have one or two cranes, and during this process, the crane is entirely occupied, and also this process involves a lot of workers. The second reason why it can cause overruns is the crane. The crane is predominantly used, as I already was saying. However, the crane also costs a lot of money. So we are trying to use the crane as few as possible, trying to reduce the time when we're using the crane on construction sites, and this is one problem. And last but not least, concrete pouring is a key process in the critical path, right? We need to first build the foundation to carry out other processes. We need to build every level before we can do like all the sub-process, so to say, and if there are some delays happening, further processes also get delays. So as this process is quite significant for our construction site, it has been monitored in the past, so starting with the 2000s or even earlier, by doing manual monitoring. So the manual monitoring was basically done with the focus on quality control. So they were checking documents like receipts, how much concrete was brought to the construction site. Was it the right amount? Did it have the right quality? By the time this further evolved, having the IoT, Internet of Things, having multiple sensors on construction sites, like this example, they attached an RFID sensor to concrete mixers, and they were able to detect when concrete mixer arrives on site, and were able to detect when pouring is starting and ending. This further developed with computer vision and artificial intelligence. So here again, the focus was not only do automatic tracking, but really nuanced monitoring to also get some idea of the productivity of this process, understanding single steps of on-site processes. And now the question is, of course, what's the next step? And I think the next step would be a digital twin construction, where we focus not only on monitoring these processes, but also be able to dynamically plan our on-site resources on time. So in case something happens, we are able to react. The construction managers are getting provided with enough information so they are able to react on time. So what are the problems right now, or what are like the key limitations of previous work, key challenges? So first of all, there is the big problem of construction sites. So in contrast to like manufacturing environments where everything is well controlled, we have like the same order of steps, we have the same environment. On construction sites, we have very different environments, right? Like different construction sites. The building is growing over time, so we might need to change the sensor placement and so on. So the method needs to be very generalizable and adaptable. And this is, of course, very, very challenging. The second thing is that previous work was often struggling detecting idling, like waiting times. Because in this case, we need to like focus on individual steps. We need a detailed method to break down our entire process, be able to detect these fine granular steps of our processes to determine potential bottlenecks. And finally, we might now know when something happened and where something happened, but of course the question is what happened, so that we can help the construction managers in the end, and therefore contextual understanding is necessary. So we need to use all kinds of data which are available to reason what were the specific reasons for our delay and can avoid these delays in future. So we believe that dynamic on-site resource coordination is possible in future. However, we think that 3 key aspects are necessary to achieve this. And first of all, as I already was telling, we need an adaptable, robust, and generalizable method to be able to transfer this monitoring method to many different construction environments. Then we need to provide semantic context, right? We need to understand, okay, which kind of resources are involved into certain on-site processes, but also understand the building products, what kind of building products were we focusing on. And finally, we need to support resource allocation. We need to support construction managers by having a flexible method so that they are able to react on all different kind of circumstances. So we decided to build a methodology based on 2 central aspects. First aspect is computer vision. So we are taking a lot of images of different construction sites using crane cameras and using some computer vision algorithms to receive information of the individual objects. And on the other hand, we're focusing on integrating this data using a knowledge graph. So being able to have information of the as-built representation about geometric information, but also about the processes. So the methodology is basically separated into 3 key steps. So we first of all have a pre-processing step, then we have a scene reasoning step, and finally a post-processing step. So first step would be pre-processing. So right, we have now some sensors on the construction site. We are getting images, a lot of images Of course, images don't provide any information, it's just raw unstructured data, and we need some algorithms. So for that we used, for example, object detection. So based on object detection, we can detect some resources, get some information, what is going on in this image, bounding box information, class information. So to further develop this information and turn it into higher level information, we need to represent this in a graph representation. And there we need to focus specifically on our processes. In this case, concrete pouring. So we decided to develop an ontological model based on the key objects which are like involved into this process. So starting with a concrete bucket, right? Concrete bucket tells us where it's currently getting poured and what kind of state is currently carried out in our process. Bucket moves, it has some attributes like timestamp or bounding box. And depending on the surrounding objects of our concrete bucket, we might know which kind of state this bucket is in. So we look in the surrounding area and we can detect other objects. So for example, a worker or a crane hook or the hose. And in this scenario, we know, okay, the hose is underneath the bucket, we know some workers are involved, so it's probably gonna be pouring in this case. On the other hand, of course, when it's maybe close to the concrete mixer, we know that it's getting filled up. So these processes are also represented in our 4D BIM model, right? We have like these 4D Gantt charts, time schedules, giving us detailed information about our processes, which also, of course, can be broken down, having expert knowledge in mind, into individual states of these processes. So we have like the when something happens covered. On the other hand, we can also use the geometric information from the BIM model, and based on the volumes, we can break down some amounts of getting concreted. So for example, we have the information of wall, slab, pillars, volume, and we know, okay, what is approximately gonna be concreted in certain areas, and we can create a link to our as performed information using a perspective transformation. So we are basically projecting the tip of the hose based on the 2D BIM representation and get the information linked together on both sides. And this can be, of course, further enhanced using semantic segmentation, focusing on the building products. So we can also receive some of the information out of the images directly, having like slabs, walls, and pillars monitored. So this sums up the first step of our methodology, pre-processing, right? So basically extracting the information out of the images and representing it, integrating it into a knowledge graph to get better understanding of our process. But now we know, okay, what are the resources involved in certain areas and where? But of course the what is still open, so right, we have the graph-based representation, but we want to know, okay, in which kind of states is the process currently, and what resources are involved in these kind of states. And therefore we looked at two approaches. So first of all, very simplified rule-based approach, having based on expert knowledge, and on the other hand, we have a graph neural network, don't providing any rules, but just learning out of data. I start with the rule-based approach. So what kind of rules did we apply? For example, for a loading stage, we can compute the intersection of a union area of the concrete mixer and the bucket, and when the bucket is close at the concrete mixer for a certain amount of time, we can assume that it's loading. Same thing goes for pouring. And based on some post-processing, knowing like the travel distance of the bucket, knowing the previous and the after state, we can reason our states of the process. So on the other hand, for the graph neural network, we need to first think, okay, how are we representing our data? And we extracted subgraphs from our data from the graph database. So in this case, we used Neo4j, each subgraph representing a scene in our process. And to give this data to a graph neural network, we need to represent this data, of course, into numerical data, having edge attributes, node attributes, and adjacency matrices. So attributes like the relationships between the objects. Node attributes can be something like the position or size of an object, and the adjacency matrix is representing the connectivity of the graph, like the shape of the graph. And then we define an architecture, train this architecture on this problem, and then the GNN can learn what kind of rules are necessary to predict these certain states. And of course, with this, we can learn way more complex rules compared to the rule-based approach. So, yeah. And then, of course, we can apply some post-processing again. So we know the order of steps. We can overcome some limitations of the GNN by applying this and getting better accuracies in the end. So finally, post-processing, the last step of this methodology I was already talking about. What do I mean exactly by that? So, for example, we have like now predicted some states based on frames in our process. So, for example, the loading phase, the moving phase, and the pouring phase. But sometimes we get occlusions, sometimes we get misdetections, and of course we need to take this into considerations, right? When we have like a computer vision approach, this quite oftentimes happens. And here we can use the information of the previous and the after image, but also the information of the resources which were detected in these images before and after. And based on that, we can reason the state and do some corrections of our previous predictions. And to represent this in a more generic way, we generated then state nodes of our processes being enabling us to query like the start and end time. So we, in the end, want to know how long did it take for the moving state, for example. And this is done by post-processing. So now I want to jump into some examples. The case study, which was carried out by us and took quite a while. So we acquired quite some data from different construction sites. In total, we had like 10 different samples from these construction sites, as you can see, from different camera perspectives. And this gives us information of 450 minutes of concrete pouring, all annotated. So quite a lot of data which can be used to investigate our method. So for the object detection, we used a data set with over 800 images, training one of the state-of-the-art object detection networks, YOLO V8X, and we used patch-wise processing to be able to detect very small objects on these construction sites. And here again, the focus is on the on-site resources. So what resources are involved in our as-performed processes. And we focused like on the concrete pouring example on classes like concrete mixer, worker, the crane hook, the hose, and the bucket. Then we also applied semantic segmentation. In this case, we had a data set close to 400 images. We used the PITNet-S model to train the network. And again, here the focus was to enhance our reasoning, right? If we can give our graph neural network more information, it probably can learn better and more complex rules according to different scenarios. And here the classes were slab, column, and wall, focusing on three different stages: rebar, concrete, and the panel stage. So this data then got converted into knowledge graphs. So what did we use to generate these knowledge graphs and the ontology models? So we used Neo4j, which is quite a common, very well-known graph database, and NeoModel to transfer the data to Neo4j. And then we use Docker-based environments, so having multiple graph servers at the same time allowed us having a lot of flexibility in testing and training the graph neural networks. For extracting the BIM data, we were using IFC OpenShell, and to get from this camera perspective to the BIM model, we were using a perspective transformation approach based on the camera intrinsics. So then this data was further converted into the individual states of our processes using scene understanding. Here we were focusing on 3 classes of our process: concrete pouring, loading, moving, and pouring. For the rule-based approach, we defined the significant area according to the bucket, to the size of the bucket. And for the GNN, we were using PyTorch geometric as framework. We defined a 3-layer graph attention architecture to detect these patterns in the graph. And the focus, again, was here on different features like node attributes, adjacency lists, and edge attributes. Okay, now I want to jump into some results of our approach. So first of all, the object detection approach. So these state-of-the-art models like YOLO V8 are very capable of precisely learning specific industry-related problems. So we got quite some good accuracy here, also across all classes when providing these, training these models with enough data. And on the upper right, you can see the tracking mechanism of our of the concrete bucket, also very, very close to the ground truth, giving us the confidence in this approach works. Then for the semantic segmentation, for the PitNet-S model, we also received sufficient accuracy. Again, here the focus was on enhancing our graph neural network approach. Then for the scene reasoning approach, first of all, for the rule-based approach, here you can see like all samples. For the rule-based approach, we were achieving accuracies of 77%, so giving a first good idea whether this approach works, and the graph-based representation supports understanding the states of the process. Then with the graph neural network, the graph attention architecture, we achieved even higher accuracies with 88.6%, so giving very good accuracy in reasoning this process actually. And again, with the post-processing, we were able to receive 92.3% for the scene reasoning, giving us very, very confident accuracy in reasoning the states of the process. Then the overall accuracy was also tested for the end-to-end pipeline. So across all samples, we received an accuracy of 91%. Here are like 2 examples shown. So we can now ground truth against predicted. So again, we are quite close at the ground truth. Also seeing we were able to detect like the individual cycles of this process, giving us a good indicator that the reasoning works. So the question now is, of course, what can we do with this method, right? So we have now a very precise method in detecting specific states of a construction process. And the first thing we did, we looked at some additional samples and looked at the process times. So on the left side, you can see like the amount of process time, and on the right side, you see like the percentage. And by closer looking at these samples, we can see, okay, there are some outliers, right? So in sample 3, we have like a huge amount of moving time. Yeah, usually moving shouldn't take that long, as we can also see it with the other samples. The question here is then, yeah, what happened? What happened in this case? Good thing is, we have a video. So now we'll have a look at this video. We'll see, okay, the concrete mixer departs from the construction site, but the process is still ongoing. And it takes time. And somehow they were waiting for the next concrete mixer to arrive. In total, they were waiting for 20 minutes. So 20 minutes doesn't seem a lot, but remember, like all of the resources are occupied, the crane cannot be used. The entire construction site was stopped in this case. And this is exactly why we are losing money and time on some of the construction sites, right? So of course we don't need to watch all the videos. We have our beautiful knowledge graph, and we can detect these kind of bottlenecks automatically by applying our knowledge graph. And this is exactly where the strength of the knowledge graph comes through. We have like a high flexibility through this knowledge graph by connecting it with the as-built data, so getting even more information about the process. Being able to extend this knowledge graph through semantic segmentation and graph neural networks. So we are able to train on the graph data on specific problems. And finally, also to improve the process insights through the knowledge graph, right? Having also the geometry data, but also very precise process data gives us very precise process insights of these processes. So now I want to jump to the discussion. First of all, we thoroughly validated our knowledge graph enhanced computer vision approach, giving us a precise reasoning algorithm. And this brings some advantages over previous methods. So first of all, we showed that it is extensible and generalizable and tested it on these 10 samples. And previous methods were just focusing like only on very precise samples, maybe having a lot of assumptions, having known the departing location of the concrete mixer and things like that. And we don't need to take this into account. Our approach is flexible in this regard. On the other hand, we are providing semantic context, right? So to further reason and further understand some bottlenecks of our processes, we need to have more information and need to also be able to integrate this data. Of course, on the other hand, some limitations need to be addressed. So with this method, we are currently focusing on visual data, depending on visual data quality and spatial relationships, right? And of course, I was already telling there are like some occlusions happening and sometimes misdetections. So in future, we believe that like a multimodal sensor data approach is necessary to overcome these limitations. But of course, again, the knowledge graph provides enough flexibility to integrate data from other sensors. And on the other hand, second of all, it's like we only focused on the crane and skip concrete pouring method, but there are also like other concrete pouring methods quite commonly used. For example, the pump-based or mobile pump, as you could see in this video, which takes quite often place on construction sites. So what I showed today was a knowledge graph enhanced computer vision approach to monitoring concrete pouring. We applied our method on varying construction contexts and stages, and we were able to interpret complex construction data and were also able to overcome limitations of incomplete data. And with this, I hope that we can support construction management with real-time information in future to build these kind of beautiful buildings on a much more reasonable price. Thank you very much. This was now I'm open to answer your questions.